So it's a pleasure to have Tian Lan speaking to us today, and he's going to speak about matrix formulation for non-abelian family. And if you have any questions, probably the easiest thing is just to unmute yourself and ask the question. We try to be pretty informal in this seminar, so whatever questions you have, just ask them. So take it away, Tian. Thanks.
Okay, thank you. This non-abelian family thing, actually we brought out this notion in an earlier paper of 3-4 years ago. And in my PhD thesis, I add some more, I proved some more details about that. And in a recent work, I developed this matrix formulation thing. And this is my outline. I will first introduce what is this non-abelian family, and recall the so-called trivial non-abelian family, which is just abelian tubular orders. And I will also conclude some results of this matrix formulation. And the main part of the talk will be divided into 2 parts. I will begin with this one-step construction. Basically, you do this construction for a matrix that is 1 by 1. And then I will discuss some properties of this special construction, and by which we can define this family, non-abelian family. And after that, I will talk about how to formulate a multiple step of construction. And you can, since there can be different paths construction that leads to the same result, I will also talk about how to figure out those equivalence relations between different constructions. Okay, so this name is named, this non-abelian family name is in analogy to the chemical family, but maybe it's more often called family groups, but group is used in mathematics and physics in a slightly different way, so we use this alternative family. So as you can see, I put a periodic table here, and there are many chemical elements, and depending on their atomic structures, the electron structures, you can divide them into different chemical families. So each column is a family, and the last one, this noble gas family, they are the trivial ones, and they are chemically inert, and they only have this noble gas cores. All the electrons outside the nuclear cores are stable, and the other families, they have the similar, actually they have the same noble gas cores, but they have similar outer electron structures. And this non-abelian family is something similar, but what replaced the noble gas is the abelian tubular orders. So the abelian tubular orders now is the trivial non-abelian family. And we use this generalized hierarchy construction as a procedure to add or remove abelian tubular orders. Okay, so, sorry. And about this trivial family, the abelian tubular orders, we have several different ways to describe them. So mathematically, you can use this pointed modulus category or metric group. But physically, we tend to use this K-matrix formulation, which is you just take a symmetric invertible integer matrix and usually denoted by K. And this diagonal entries should be even integers. And then you can calculate all the data of the anyons using this K matrix. So firstly, the anyon types, the anyons are represented by the integer vectors. And if two integer vectors differ by the column of K, or integer or multiples of polymers of K, then they are the same type of anyon. And to fuse to abelian anyons, you just add the vectors, and the topological spin is just given by the inverse K as a quadratic form.
Excuse me.
Okay.
Can you explain like what do you mean by, like, when you say anyons are represented by integer vectors? Like they can be represented by arbitrary integer vectors?
Yeah, arbitrary integer vectors, but up to an equivalence relation.
Okay, I see. Okay, thank you.
Yeah, because this KK thing will give you trivial statistics. So that's trivial anyon.
Okay.
Mm-hmm.
Thank you.
Okay, and actually to relate to the maybe most mathematicians more familiar with this metric group. So if I give you a K matrix, then the corresponding metric group is just you take first a free abelian group whose rank is the same as a K. Then the quadratic form, the non-degenerate quadratic form on this K is given by this formula, which is just the spin. You take exponential to the spin. And then your actual abelian group is this zk mod out this kzk. So you view K as since it's a matrix, you view that as a linear transformation of zk. And then qk is this quadratic form, give you the topological spin. Also, physically, we have some alternative descriptions using either unit field theory, the Tian Lan theory, and this K appearing as the coefficient, or use this effective wave function, and this K appear as the power of the coordinates. Okay. So now, for this non-abelian family, we can actually do something similar. In following, I will show you, you can actually represent the difference between any two topological orders in the same non-abelian family by, again, a symmetric invertible matrix K together with a vector of anyons, of abelian anyons. And in particular, if you choose this difference between two, so we choose one of them to be a root. So this root, by definition, is the topological order in this family with the smallest rank. If you choose one to be the root, then all the other topological orders in the same family can be efficiently generated by this root together with these two data. So just a sequence of anyon and a matrix. And this K matrix, if you choose one to be root, this matrix will be an integer matrix.
So,
and its diagonal entries will be even or odd depending on this anyons to be boson or fermion. So question, please.
oh yeah, okay, I think you just answered the last sentence. So you don't require K to be a even matrix.
No, but so this root is alternative definition or property. There's a pointed subcategory of this root. Also, abelian anyons, they form a symmetric fusion category. So if this A are in the root, they has to be boson fermion. So if it's a boson, this corresponding diagonal entry should be even. And if AI or for AI is a fermion, then KII should be odd.
So also the kappa. So you have a series of abelian anyons. So
Yeah.
that means each AI that itself is a vector. Well, I think
each one is abelian anyon. This both A is a vector.
So this is a matrix of certain size.
No, this A is a vector. So this
it's a vector of a vector.
it's a vector of abelian anyons. So just a formal notation. So each entry is abelian anyon.
Okay, so if we formulate the abelian anyon by Kim matrix, so that would be another
in that
vector.
case that will be a matrix.
Yeah, well, it's a
but
matrix.
here this AI, this A1, A kappa, they are just abstract symbols.
Okay.
My understanding is that those A1, A2 can be repeated, right?
That's right. Yeah, it can be.
A1 can be trivial anyon. A2 can also be trivial anyon.
Yes.
That's also allowed. Okay.
But maybe since we stopped you already, so what's the kappa? How do we decide the kappa? The number.
Kappa is just of your choice. It can be any integer.
Okay, so it's undetermined.
It's undetermined. Yeah.
Okay.
Okay, so to start, I will begin with the case that kappa equals to 1. So I'll call this a one-step construction. And well, we start from some topological order C, and at this stage, I only list those invariant quantities, not rigorous category. So this fusion rule spin, central charge as T matrix, and I'll tell you how these quantities change. But later I will give you a more rigorous formulation. And how we do this construction? Basically, we have two choices. One abelian anyon, I would use AC, and then even integer, MC. These two are of your choice. You can choose arbitrarily. AC, but AC abelian anyon AC in this order, and any even integer. And each choice will give you a different new order. And besides that, we also need to compute these mutual statistics as rational numbers. They appear as in the power. So of course, here there are some choices, but we use those as some gauge choices. You can choose the TIAC, so differ by some integers, but the result will not be. The result doesn't depend on this choice of mutual statistics. And the basic idea is we let this AC to form some Lofting-like state whose power is given by this big MC. Big MC is just this given integer minus the mutual statistics of the AC itself, or just 2 times the spin.
This mutual statistic is a rational number, right? Here is a rational.
It's a rational number, and this big MC is a rational number in general.
But do you choose this rational number to be 0 to 1, or can be outside 0 to 1? Or there's
that depends on the AC, depends on spin.
Okay.
So this MC must be even. So this capital MC is a rational number that depends on the spin of the anyon of your choice.
No. Okay, I didn't get your answer. So the SAC is not determined modular integers, right? So how do you choose the integer part?
So I don't quite get the question.
Well, the question is, AC is a abelian anyon, so it has a dimension SAC.
Mm-hmm.
That's only defined modular integers.
Yeah, but you also choose this small MC, and if you shift those together, that give you same answer?
Well, my question is, do you have a, is SAC, it's the same question that Xiao-Gang asked. Is SAC between 0 and 1, or you can choose arbitrarily integer part?
You can choose arbitrary, but that's a change the meaning of this MC, this small MC. So only their difference, this big MC, determines the final result.
Okay, then for your S matrix, what is your 1-1 entry of your S matrix? Yes.
This is normalized.
It's normalized or not normalized?
It's normalized.
So it's
normalized.
1/D.
But it's not that important in this construction.
Well, I don't, but it's determined the T. So it's we just want to make sure. So your S matrix is normalized.
It's normalized.
So the first entry is 1/D. Okay.
Yeah, it's normalized as shown here.
Okay.
But it's okay to choose SAC to be from 0 to 1. You can always canonically choose that, right?
Yes.
That's right. Yeah.
And also you can choose this T.
You can fix your gauge. Yeah.
The fixed gauge. Yeah.
It's fine. You can fix your gauge to choose everything to be between 0 and 1.
Okay.
Except this self-neutral statistics. So it has to be choose to be 2 times spin.
Oh, okay.
And you have to first choose spin and then choose this diagonal thing.
Okay, I understand.
For example, if it's a fermion, similarly you can choose this to be 0, but that's not the case. You have to choose to be 1.
Okay.
This T has to be 1 for a fermion.
Okay.
Okay, so basically this you have to choose. Strictly speaking, you have to choose this AC, MC, and some neutral statistics. But finally, what determines the construction is this AC and this capital MC. And the new anyons. Also, and I will denote this Newton order by this C subscript script with AC, MC. And the anyons in this Newton order are given by this pair, I and M, and I will call this M a flux. And I is any anyon, including non-abelian ones, any anyon in C. And this M has to be, if M plus this neutral statistics, it has to be an integer. So it's integer shifted by neutral statistics. And besides that, we also impose this equivalence relation is that basically saying this AC MC is a trivial anyon. And if you fuse this trivial anyon to IM, then you got a equivalent anyon.
Okay, I want to go back to your item 2. So it's always possible to choose the T, the self or mutual statistic TAC-AC equal this twice SAC. That's always possible?
Yeah, it is.
It's not obvious to me that's possible, always.
So this question just simply tells you cannot choose those things independently.
Well, it's not independent. The TAC and the SAC.
Yeah, you basically choose this spin and then that determines this diagonal TAC. But for the not often diagonal ones, you can choose them freely, just up to integers. So this TAC has to be up to even integers, if you want.
Well, I don't know. I don't know. Obviously, I cannot see. So both the TAC-AC and the twice SAC, they are determined up to integers. So
yes.
You are claiming they are the same, basically, up to integers.
This is a constraint. So I put that in the construction.
Well, so you require that to be true.
I require that to be true. Yeah.
Okay, that's better because I don't see why they should be true though. Okay, so it's a requirement.
Yeah.
No, it has to be true because the spin, self statistic is like exchange two particle. And this mutual statistic is go one particle around another particle by 2 pi. One is pi, another is 2 pi. So there's a factor 2 difference.
Yeah, so yeah, if you really compute them, for example, in the K-matrix, in a physical process, this has to be true.
Well, I know this is true for abelian anyon theory, but I don't know, obviously, maybe it's still true for, abelian anyon inside a non-abelian theory. So that's why I asked the question. I know this is true. If you have a completely abelian theory, that's always true. Okay, anyway.
Yeah, so here you can think that as a requirement. We don't choose this diagonal mutual statistics independently.
Okay.
Okay, and to determine this new theory, I'll give you this fusion rules. It's just fuse so IJ are just anyons in C, fuse them, and add up to the flux M plus L. So there's a fusion rule, but this is up to this Krim's relation. So it's not final. We have to further pick some representative and impose this relation. The spin here is just the spin of I plus this flux, spin of this flux M. And
okay.
Okay.
I have a good question. So you say I is in C is just an arbitrary, maybe simple object, I should think of it. Does every simple object appear? So there's a choice of M for every I?
That's right.
Okay. So that's so you you can think of it
as long as this
I.
M is, so basically this M you can choose basically in the integers, but shifted by this mutual statistics.
Right. Okay. Very good.
But if you further analyze that, you'll see there's only finite many M's are inequivalent because of this Krim's relation.
Okay.
So this
thanks.
AC has a finite period.
Right.
So yeah.
Very good. Thanks.
Okay. So next I will tell you how to tell you the physical motivation of this construction in terms of this effective wave function. So I will use this notation. It's psi A ZA for this mu M2 for a quantum state on the manifold with anyons of charge, the psi for the anyon charge or the excitation type, and ZA for the position. And this mu is because if you use some non-trivial manifold, then there will be logical degeneracy. So you need this additional label mu. And by an effective anyon wave function, we just add those states up with respect to this coefficient. And in this talk, I will just consider the simple case that all these psi A's are abelian anyons, and this manifold is a sphere. So I will keep only this two symbols. And as a first example, if you consider Anyon condensation that corresponds to such effective wave function, that if this psi A is a condensed anyon, then its wave function is 1. This is not normalized, so it's 1. And if some of these psi A are not condensed, then this wave function is 0. So this means this effective wave function is equal wave superposition of all the condensed anyons, and they are in a 0 momentum state. And since this wave function has a product state, tensor product state shape, so we may also call this condensed anyons form a trivial state.
excuse me. So here, this is C A, just A label different, and I mean, the same type of anion, but a different copy of them, right? So you only have
this A, I use A is just some abstract index. So this A means at the position ZA, there is an anion with type CA, and they can be repeated.
So the CA is anion type, ZA is anion position. Okay. Yeah. Okay. Thank you.
Okay. So this is a example that anions form an effectively trivial state, and that's just a boson condensation. And for construction we are interested in now, we actually want these anions to form a Löffling-like state. So that means this effective function. So at position ZA, you output the same type of abelian anion EC. This is what you choose at the beginning. And then the polynomial part of this effective function is like a Löffling wave function, the minus ZB to the power MC. And of course, this MC is has to satisfy some condition that is determined by the statistics of this AC. For example, if AC is a boson, then MC has to be even integer, and AC is a fermion, and MC has to be odd integer, like the Euro-Löffling wave function. But now we want to choose this AC to be some not some really anion, abelian anion, not boson fermion. So I have to analyze how this MC can behave. So first thing, if we consider exchanging to AC anion, then we get two phase factors. One is 2 pi and MC over 2. It's from the wave function, and the other part from the anion statistics, just 2 pi times the spin of AC. Then we conclude. So we want this wave function to be single valued. And we conclude this MC over 2 plus SAC has to be an integer. Then so in fact we that also means if you multiply both sides by 2, then MC plus 2SC is even integer. So this 2 even integer is what we this is the second parameter we want to choose for our construction. Okay, and that's for this MC of this wave function. And the other thing is, well, we also want to analyze what kind of excitations can be in this effective wave function, and we use a similar method as what we analyze the Cauchy holes in Löffling wave function. So a similar Cauchy hole excitation in this wave function, we can put so this Z prime.
做题挺好看的，它是应该用 lattice 做的。
Sorry, do you have a question?
Yes, somebody said
Okay.
something I couldn't hear.
Probably they were just unmuted.
Okay,
Okay,
Oh, just continue.
I'll continue. So
let's continue.
here this Z prime denotes the position of the Cauchy hole, and you can so it can be equipped with a flux n, and also at this position you can have any anion I at this Z prime position. So Xi prime is with anion charge I, and that's will give you such a wave function. And again, this m of this power m cannot be arbitrary. It also depends on the mutual statistics. And similarly, you consider moving this AC, this in the ground state is a trivial AC around this quasi hole. Then you obtain two phase vectors. One is 2 pi I m, and the other is a mutual statistics between I and AC. And then similarly, you conclude m plus this TIAC must be an integer. So that's the constraint for m.
So question here. For the equation you put there, e2 pi I, TIAC equal this D thing. Why you have a bar? Where the bar came from? In the S matrix, you have SIAC bar here. This bar here. Why there's this bar? This thing here.
Sorry, I didn't hear. My network seems to have some problem.
Yeah, okay, so the formula is E2 pi I TIAC equal D, and then the S matrix entry.
Yeah.
Why you have to use bar, the Anyon bar? Is there a reason?
There's AC bar.
Where the bar?
This AC bar.
Yeah.
Where the bar comes from?
That's some convention thing, because actually, I picked this convention at the beginning.
It's a convention, or you have to?
So because A is pointed, so if you take A tensor AC bar, you will get the tensor unit. That makes sure that your the equation T equals to 2S is true.
Yeah, I think that part is the reason, but
I think it's a convention because when you define the phase of an S matrix,
it's kind of a phase of a S matrix.
Anti-clockwise. You need
okay,
to.
I don't know there's any significance. It is a complex conjugate.
The wave function always defined anti-clockwise.
I don't know if it's a convention or just say there's something meaningful. But anyway,
so this is basically a convention of S. So if you define S like something.
Or maybe it's your
if you define S like this, you have to take this bar. But some people don't define S like they use different orientation with these loops. Then
it's not that it's not their choice. They made I would consider this a mistake by doing the other way. But anyway, okay, go ahead. It's one choice of something.
Yeah, so it's meaningful, but it's depends on some other convention.
Yeah, okay, maybe it's the convention of your S matrix.
Yeah. Okay, so next thing you can compute the spin of this quasi hole, but I didn't show that. But I think it's similar like how you compute the spin of a quasi hole in the Leibniz wave function, and it turns out to be the spin of I plus the spin of this m flux. Its formula is m squared over 2mc. This mc is the power in the ground state wave function. And it's obvious if you want to fuse two quasi holes, you just put this ij together and then as the Euro fusion and adapt this flux. But you also notice if I say excitation is AC with flux MC, that simply gives you a ground state wave function with an extra anyon. So it also means this ACMC is a trivial anyon. So that gives you this equilibration. So this basically finished this construction part, and I will tell you some properties of that.
So this fusion rule you described before automatically compatible with this equivalence relation, right?
Yes.
Because yeah, this is a fusion rule. Yeah, you have this fusion rule.
It is automatic. Yeah. Okay. So the first thing I want to clarify is that this construction, although I only show you some basic properties, basic quantities, is valid at the categorical level, and I will show you like at this section. And also, we don't need to construct that for modular tensor category. We can do that for any braided fusion category. And the second important property is that this construction is reversible. So in this CACMC, you can choose the unit flux. That's a trivial anyon with flux 1. And you choose this AC prime, this unit flux as AC prime, and the MC prime as -1 over MC. You can verify that this satisfies the constraint that I gave you before. And then after these two constructions, you go back to C. So this is like a reverse construction. So since this construction is reversible, we can use that to define an equidistant relation between two order orders. That if two order orders can be connected by several steps of this generalized hierarchical construction, we see they are equivalent. And the orbit of this construction, or the equivalent class, is what we call the non-Abelian family.
Do you know that this procedure is independent of the order of the anyons you choose?
Oh, that would be...
What I'm saying is that if you start with the modular tensor category, there are few abelian anyons. So you start to choose one, you start to do hierarchy until you get rid of all of them. But there's an order here. Do you know they are independent of the order?
That's part of an open question, and that's why I try to develop this matrix formulation that basically want to study what kind of results if you do multiple steps and choose different anyons, different order.
Okay. This reminds me basically, it's I think it's some kind of generalization of gauging, because abelian anyons, I think they are in one-one correspondence of natural transformations of the identity functor. So it's some kind of symmetry. So I think I don't know, it's our theorem or somebody else's theorem, but the abelian anyons are in one-one correspondence to natural isomorphism between the identity functor of the modular tensor K self to itself. Actually, it's definitely in our papers, and so I think that there's a construction of those things. Maybe you have to be a little bit more categorical higher than we did in the gauging paper, but it's much like that kind of thing.
I see.
Anyway,
that would be very interesting.
The reason I mentioned gauging is the same problem there. Is gauging could depend on the order of your gauging. So
yeah, of course, yeah. It depends on the order, and so now I think it's an open question that how these different orders give you different, whether they give you the same thing or different things.
Well, you definitely can generate an equivalence class, but it's not clear,
Yeah, this structure of this equivalence class is not clear at the stage of this.
Yeah, that's why you can generate an equivalence class, but it's not clear, what this thing gives you.
Yeah.
Okay, good. Okay.
So this when you say this abelian anyon correspond to some kind of symmetry, and
that's a theorem actually. Yeah, it's a theorem that all the abelian anyons is one-one corresponding to natural isomorphism of the identity functor to itself. So it's some kind of
symmetry of the automorphism of a braid diffusion category, or you talk a different thing?
It's one categorical higher than tensor equivalent.
Oh, it's like automorphism of the identity functor.
It's the automorphism of the identity functor.
Okay.
It's one categorical higher than what we did for gauging.
I see. Okay.
Okay, so there's some other property. So you can compute the rank of the constructed thing. Is the old thing multiplies the absolute value of this MC. Remember that this MC is just even integer minus 2 times the spin. As long as this 2 SEC is not 0, 1, or AC is not a boson of fermion, then you can always choose a particular MC, a particular even integer to make this big MC to be between -1 and 1. And after such a construction, you can reduce the rank. So you can always reduce the rank, reduce further, and since the rank is have to positive, so this tells you there's be some. By this procedure, you can get a topological that has the smallest rank. But if you check that more carefully, you will see if there are abelian anyons that have non-trivial mutual statistics, you can also reduce the rank by 2 steps of generalized current construction. So we conclude this. So actually, we'll make a definition that we call the smallest rank among non-Abelian family as the root topological orders. And by this argument, we also know that in this root topological orders, all the abelian anyons must be boson fermions, and their mutual statistics has to be trivial. Or mathematically, we see this pointed subcategory is symmetric.
And you also don't know this is unique, right?
It is. We know it's not unique.
It's not unique. Okay.
It's not unique.
Okay, good.
And also, is it clear why MC absolute value MC times the rank of C is an integer?
So you mean why this is integer?
Yeah, because you said that's the rank of the resulting.
Yeah. Why is it integer? It's actually quite clear because this MC times NC must be integer, right? And this 2 SAC. So this is spin times the period of AC has to be integer, and the period of AC has to be a factor of the rank in C, right? So.
If C is a
so you can think that basically NC times SAC has to be integer. So that change AC into a trivial anyon. It has to be, right?
Okay.
Yeah, you can it's not very clear, but it's just some easy analysis. Okay, so other properties. First thing is quantum dimensions. Just remain the same. That doesn't depend on the flux we add. So this quantum dimension is kind of property of non-Abelian anyons. So so basically this tells you this construction kind of preserves the properties of non-Abelian anyons. And the second one is central charge. Central charge, we can prove that it changes by the sign of MC. So it changes by plus or minus 1. So in other words, for non-Abelian family, this fractional part of central charge is invariant. And the third thing I list here is a bit more involved. So if you think consider an anyon AI whose mutual statistics with EC is trivial, then in the constructed order, this I with zero flux will have the same self and mutual statistics. So then we can conclude this mutual centralizer of all the abelian anyons is invariant. And clearly there should be some more properties, but for now we don't know. Okay. So here I'll give you some examples, and this is for the abelian family, and it's also for any non-abelian family if the root contains only one abelian anyon. And basically this is the root, and if you do some constructions, so each edge represents one step of construction, and this point is at word order. So you can already see here that the central charge that moves by one, and the rank also. So there's some pattern here, and in this table, this red entry represents this mutual centralizer abelian anyons. This red entry, and the others are the spins and the rank. So this is the trivial family, the abelian family, and this one is this named by one of the root as SU2 level 2, or the Ising. It's the Ising non-abelian family, and you have trivial anyon and fermion in your root, and there are 8 of them. And if you do this construction one step, you'll go to twice the rank, and there are still 8 of them. And you can I didn't draw the upper things, but basically it's like this. And the third thing is this SU2 level 4 family, and they have the root has a trivial anyon and a Z2 boson, and there are 2 of them, and the lower rank 12 orders in this family looks like this. And this spin 1/3 is it has trivial mutual statistics with all the abelian anyons, and it's the same it's invariant you can see here.
So this is true in general, that the total quantum dimension d square is always a multiple of the root?
That's true. Yeah, the d square changed by the same factor as the rank.
Okay, the same factor as the rank. Okay.
Yeah. Okay, and that's basically one of the motivations that why I want to figure out the structures of these patterns, these graphs, or of the equivalent class. And as already mentioned, if the root has only trivial abelian anyon, then the root is unique, and this family is just a stacking of the root with the abelian family. And the abelian family is efficiently described as this K matrix. And if your root has a fermion, then it has this pattern of 8-fold weight. And if it's Z2 boson, you have 2 roots, and you have similar pattern here. So basically, this pattern is determined by the abelian anyons in the root, and together with some kind of K matrix things. So let's continue to this multiple step construction. And as a motivation, I will first remind you this K matrix for abelian equal order. They are described as K matrix. So in this special case, if our C is corresponding to the matrix KC. Then if we choose AC to be some abelian anyon, in this case, just integer vector is LC, and choose some EV integer MC. In the neutral order, with this after this construction is just described by the K matrix KC with one more column and row, and this one more column is just given by this LC and MC. So you can think about this K matrix formulation. You can think this KC is also constructed this way. So you from a trivial to order, it's derived by a 0-0 matrix, K matrix, and you do a one-step construction, and you get a 1-by-1 K matrix, and you further continue. You got this. You can get every K matrix. So you can see this K matrix actually records the information of the steps how an abelian order is constructed from a trivial root. And we want to do this thing for other non-abelian families. But if we do that in this like step by step, we have to compute this mutual statistics, and that is very involved. So we want to kind of get rid of that. We actually record the integers, which is a flux plus the mutual statistics, and we don't compute this mutual statistics at in the intermediate steps. And the procedure will be like this. If the first, if you start from some C, and the first step we take abelian anyon and an even integer, and the second step you will take abelian anyon. That will be abelian anyon in C, and with a flux. That flux is any integer. It's k21, and you also need to choose another even integer, and you can repeat this procedure. You will get something like this. So a sequence of abelian anyons, and the diagonal entries are even integers and some other integers. And in the end, what we use is a K matrix, but it's not this integer matrix, but that integer matrix minus the matrix of mutual statistics. Is computed in C. And this construction can be, you can verify that using this multi-layer effective lofting wave function, which that you have if you do a kappa steps of construction, then you form a kappa layer wave function, and in the ith layer you put AI there, and the power here I should put this I should put A smaller than B here, so that the thing doesn't repeat. So power is this matrix, and by a similar analysis, you can see this power has to satisfy those two conditions. You can get these conditions by exchanging anyons and braiding anyons of different layers. So basically, this Kij, so off-diagonal entries must be integer shifted by mutual statistics, and the diagonal entries must be even integer shifted by 2 times spin. And in particular, if C is a root, then all this Ti, you can choose all these T to be integers, and this 2Si is some even integers. That's reduce K to be an integer matrix, and the diagonal entries is even or odd depending on the corresponding anyon is boson fermion. And also the new anyons are given by the pair of I with a vector, and this vector, again similar analysis, this vector plus the mutual statistics has to be integer. But this is basically a vector. This vector and mutual statistics is a vector, as I are the indices. Okay, so to conclude, not to conclude, these are other properties of this construction. It's basically you just replace AC with this vector and MC with this K matrix, and also the flux with this L integer, and everything just the same form. This accumulation, but you have now you have kappa of them for each column, and the fusion is just the fuse first and add the flux, and the spin. Spin is now given by this matrix product, and S matrix is also the old one multiplied by this this phase factor, and with additional normalization. And also the rank changes by the determinant of K, and the central charge changes by the index of K. So the positive eigenvalue, the number of positive eigenvalue minus the number of minus eigenvalue. And you can prove that this is the same as kappa steps of one-step construction by induction. But I'm not going to show you that. Instead, I'll tell you this more rigorous formulation. So let me first fix the notation that C is a braided fusion category. It does not need to be a modular tensor one. Any braided fusion category is fine. And alpha and C for the associated and braiding, and underlined C point for the abelian group corresponding to the point in the subcategory. And also I use this T to choose the mutual statistics. So it's from the simple objects to and the abelian anyons to rational number. So kind of some choice here, but the final result that does not depend on this choice. And also I will use this Z kappa for a free abelian group. And I will view that as a vector space over rational numbers. And then this due, this Z kappa bar as the due space is the function from Z kappa to the rational numbers. And now the xy for elements in zk and fg for the functions. Okay. Then this basically a standard thing. If I choose a non-degenerate symmetric bilinear form, then it defines a isomorphism from zk to the dual space. And this you have an inverse map. And this inverse map also determines a bilinear form on this dual space. And the other thing is we want to choose the kappa anyons. But now we use this group as group homomorphism from the kappa to this abelian group, and denoted by this bold A. And the fact is a group has homomorphism because you can remember this function, you can recombine the layers. So basically this addition here just means you recombine the layers. And the group automorphism of this C kappa means a recombination of the layers. And this integer condition now is transforms to these two conditions. So basically the diagonal entries is even integer and the others are integer. And our goal is to construct a new category that is kind of a semi-direct product of C and this Z kappa mod of KZ. But to do that, we first define an auxiliary category, which is a graded category, and the grading is by the dual space quotient out by this K of 2 kernel A. And in fact, I think you can directly study the grading by Z kappa, but quotient by this subgroup is just to make things finite. And this tool is, our natural tool here is to make the expression simpler. So this component in this graded category, if you take a function as a component, is a full subcategory of C with simple objects satisfying this condition. And this just flux condition you already see. So this flux plus mutual statistics has to be integer. So this component is consists of all the simple objects satisfying this condition. And then in this auxiliary category, we can define the tensor product and the braiding. So product is just fusion and flux at together, the grading at together, and the associator remains the same. The braiding is just the original one times the phase factor given by this binary form in the dual space. And you can prove that this braiding is independent of the choice of the representative. So because we quotient out by this subgroup. And this auxiliary category is a braided fusion category. And the next step we want to, so because this AX and K with this flux of KX is a trivial anyon. It should be a trivial anyon, and you can verify that in this auxiliary category, these anyons are self-boson and they have mutual trivial statistics to any object. So that means you can they generate a symmetric fusion subcategory in the mutual center, and you can, and that's a Tian Lan category, and you can condense all of them. And after you do that, after you condense all of these anyons, this is our final result. And the flux range is now reduced from this auxiliary thing to really the kappa mod of K. And because it is abelian anyon and they are in the mutual center, so doing this boson condensation preserves the fusion and braidings and also the TS matrix. But the completed thing is F matrix. So F matrix get completed, and it depends on the choice of representative. So this is why I choose 2 here. So for the 2, I can choose the associator to be the same. But if you after this boson condensation, you can no longer do that. Okay, so this is a rigorous formulation. And with that in hand, what we really want to do is to study how this the internal structure, how these patterns of these non-abelian families. And there are 2 very apparent equivalence relation. Basically, one is the equivalence between the starting category C and D. And if you have equivalence like that, then the constructed ones are also equivalent if you apply this F to the abelian anyons. And the other thing is the automorphism of this Z kappa. Automorphism of Z kappa. And in terms of some basis, it's just a kappa by kappa integer matrix whose determinant is plus or minus 1. And if you apply this transformation, you apply that both to this A and to this K matrix, and those things will be equivalent. And some non-trivial things is this reversibility. So if you do these 2 steps of construction, this 2x2 matrix, first choose AC and then trivial anyon and some MC, and then you can transform this K matrix to by this WW, this GLZ transformation to this minus 2 times spin and 0, 0, 0, 1, 1, 0. And you can verify that this gives you the same category. And I will call this special thing as a trivial bilayer. So this is a conjecture. when will this CA and CA prime K prime to be equivalent? And the conjecture is up to the automorphism C and GLZ transformations. If they can be transformed to such a form that this B and B prime are just trivial bilayers. So if this holds when we conjecture, actually we conjecture this is all the possible constellations. So this somehow in analogy to the equivalence of the integer bilinear forms, but basically we just didn't find other possible constellations. And there are close related problems that will, how can we find somehow some canonical form of AK under this GLZ transformation? And you know that if for the trivial family for this Abelian anyons, you have this E8 state that gives you trivial statistics about the trivial central charge. And what happens here? Because you can choose K to be some E8 matrix, but this sequence anyons may not be all trivial. So, well, what kind of things will that tells you? And the other is harder, that if you have two Taylor orders, how can you determine if they are in the same family, and how can you like write down this construction A and K? Okay, so that's basically a talk. And for in construction conclusion, maybe I just emphasize here. If you want to classify all Taylor orders by this construction, you just need to classify the root Taylor orders. And the root Taylor orders, by definition, are those Taylor orders whose Abelian anyons form a symmetric category. Yeah. And questions?
Oh, we are done.
Yeah.
Yeah, thanks for the talk.
Thanks.
Yeah, if you have any questions, just unmute yourself and ask away.
I do have a question, but I let other people ask first.
I have a quick one. So, so if your root has only the trivial object as an invertible, do you have a description for those, for the hierarchy, for the family?
Oh, that would be by the Euro K matrix.
I see.
Yeah. So because you can only choose the trivial anyon. So
right.
basically,
right.
this A becomes a trivial, and that's the Euro K matrix formulation.
Okay, very good. Yeah, and maybe another related question. So it looks like when you're doing this, at least from the tables that you constructed, you can start from a root and then sort of build these larger categories. And you were saying something about how like often the fusion rules and the S&T matrices are all identical, but just the associativity changes. Is that?
Yes.
Like maybe this happened.
Yeah.
Yeah,
this
right.
happened if you take this range.
Right. Okay. So
so if you can also do that if you drop this 2, you can do that in the half range, and in that case, this alpha has to be modified by some ±1 factors.
I see. Okay. So it's just ±1. So that's
yeah, that's ±1. But if you further do this thing, then it's hard to describe.
Okay. But it's like an associativity twist, right? So if you have a graded fusion category,
yeah,
often you can do this. So that's what it looks like to me, anyway. Yeah.
And if you, in fact, if you don't mind this finite thing, you can just do that in this Z kappa. and things will be also true. But you will do a condensation of find infinite many anyons, and I don't know if there's some problem with that.
I see. Yeah, thanks. Other questions people might have?
Yeah, so let me check a few things first before. So let's talk about the easiest case, which you call, what is condensation anyons or something. You start with a single abelian anyon, and then you do this procedure. So I just want to check two facts. One is that the rank is always multiplied by this integer or this rational number MC. Is that correct?
Yeah, that's right.
And
the rank and the total quantum dimension.
The total quantum dimension is also multiplied by this d squared, right?
Yeah.
Or this MC.
Yeah.
But you can choose this MC to be between -1 and 1.
Yeah, if you have this.
Well, that confused me because
this AC has if AC is not a boson fermion. So that means if you choose a non-boson fermion AC and a appropriate even integer, you can achieve this. There's basically only one choice.
Okay, well, the thing is, if you choose MC absolute value less than 1, that means your rank is always reducing.
Yeah.
But that confused me because that means that you get a smaller category. But normally,
you get a smaller category.
Normally, what it does is that you take an anyon, you add some fluxes, and those all have the same quantum dimension and everything. But
yeah, that's right.
And then in this particular case, you will have a category which is a d squared smaller. Is that right?
That's right.
That's a little bit of strange because the examples you gave, they all have a bigger d squared, right?
Yeah, so you have infinite amount of ways to increase the rank, but only basically one way to reduce the rank.
So it's not in general that the category can be made bigger or smaller. It can go either way.
Yeah, it can go either way. So you can check, like for example, here you can go up or down, but down basically is also only one way. So upper, there are actually many ways because I cut off the rank by 6 times.
Okay, I see. So
if you choose a large M, they can be very big rank.
The reason it's so confusing to me is I still think this is a generalization of gauging.
Mm-hmm.
So it seems like your procedure does two things at the same time, which is both is condensation and gauging. So in terms of the case of a finite groups, which there's a studied theory, and when you do condensation, normally your rank goes down and your category becomes smaller. If you do gauging, your rank goes up and your category becomes bigger. And the central charge does not change mod 8 and the quantum dimension change as you described. So the procedure you have seems to be either way. They are both the same thing, which is, the central charge now you generalize, instead of always change by 8, the central charge can change by any integer, but
yes.
you cannot change by fractions. You can only change by integer.
Yes.
The quantum. So I think this is something like, in your general procedure, you have this new category. What do you call? You called I forgot the notation. CAK. There's an arrow cut. That seemed to be.
You mean this formulation?
So, yeah, the formulation. You have a category. The first.
Yeah, it's just an intermediate step.
No, let me check on that one. That category is not braided, right?
It's braided.
It is braided or not?
It is braided. It is braided. I can define the braiding. Yeah, and with this definition, you can check the hexagon equation. That still holds.
I would guess it's only G cross-braided. So maybe there's a further generalization of your construction. Because I think what this category is kind of in the middle, which is, you start with a modular tensor category if you have a finite group symmetry. And in the process of gauging, the first thing you do is add the flux to get a G cross-braided category.
Mm-hmm.
I think your CAK is the same as the G cross category. But in general, in that case, it's only G cross braided. But you have a braided category. So,
It's braided, yeah.
So maybe this is not the most general setup then. Maybe there's a further generalization then.
Is it true that you can move from like dimension 4 to dimension 5?
Well, it's not clear because you have to.
It depends on the spin of your abelian anyons.
Yeah, it depends on MC. MC tells you the fraction of the ranks.
Yeah.
Mm-hmm.
And it's also actually for those we are thinking about this. I think the Galois group of the category does not change because the quantum dimension does not change. Or maybe
that is the question I want to lead to. The quantum dimension does not change.
So maybe
the ratio of SIA over DI. I think that is what matters, right?
Yeah, you're right. It's a normalized column.
Yeah.
So maybe they do change.
I think it does because it looks
under
like
Galois group action, what happens? So that would be really interesting.
Yes.
I mean, in the abelian family,
we probably can change.
In the abelian family, it looks like you can move from like a trivial category to anything.
Yeah.
That is, yeah. So you can get.
That's true. That's true.
Right.
That's true. Yeah. The abelian family has lots of Galois.
Yeah, so there's a very very wild equivalence. All the abelian things can be removed.
Well, I think that's actually a pretty interesting question because this has a physical interpretation, the hierarchy construction.
Yeah.
So it's very unnatural mathematically. Maybe that's the point. Understand this. I still think this is a gauging of a 3 group.
I see.
Probably, yeah.
That would be interesting to real.
I think it's a gauging of a 3 group because this is just a gauging of the natural isomorphism of the identity functor.
I see.
Which in the standard gauging, that's considered to be trivial.
I see.
So I think this is definitely beyond standard gauging. So because it's change central charge by integers, not by multiple of 8. So.
And the just mention here is this: the Mueller center is also invariant. Yes.
Yeah.
If you start from some because Mueller center contains in this category, yeah. If you start begin with some premodular category, then the Mueller center stay the same.
I think the Mueller center, the mutual center can have non-abelian anyons, right?
Yes.
Yeah.
So maybe that's the right. Okay, maybe this is what I'm looking for. So if you take the pointed subcategory, you find it's a Mueller centralizer. It's not a Mueller center. It's the Mueller
centralizer. Yeah.
You find the Mueller centralizer of the pointed part.
Yeah.
Yes.
That's some category, and I claim that's a symmetry of the modular tensor category. You can gauge it.
Okay, that makes sense. Mm-hmm.
You mean this? You mean this?
I mean the Mueller. That's always I want to do, which is a gauging categorical symmetry.
Okay.
I'm proposing the Mueller centralizer of the pointed part as the category to be gauged.
What do you mean by gauging that category?
It's just that if you have a modular tensor category, you can always find the Mueller centralizer of the pointed part.
Okay.
And that's a subcategory. Is that a subcategory? I think
It's adjoint. That's an adjoint.
Adjoint subcategory.
that's the adjoint subcategory.
Yeah, that's the adjoint.
It's a trivial component of the grading.
Yeah, yes, this is the adjoint.
Yes.
Oh, this is okay. Maybe. Okay, so I think then this is the pointed part. Abelian group is the universal grading of the modular tensor category. And then the Milger centralized the pointed part is just the trivial grading in this grading.
Yes.
So the trivial component.
Yeah.
Oh, maybe I think I got it wrong. Maybe I should consider. Maybe the pointed is the symmetry. It's gauging that one actually. It's gauging the. Okay,
Yeah,
maybe that's the right formulation. So,
yeah.
Take any modular tensor category, and the universal grading is the pointed subcategory, which is a group.
Yeah.
And we should consider this as the symmetry of the adjoint subcategory. And gauge
Okay. I see.
I think that will agree with, the gauging formalism before. And the difference is that in the old formulation, the abelian group has anomaly because they don't always lift it to tensor functors autoequivalence. And here, every abelian category mapped to the trivial tensor functor identity. But they have a further non-trivial thing, which is the natural isomorphism identity functor.
My goodness, okay.
And that's how you get, that's your gauge it. You gauge a categorical 3 group, which is a trivial up to tensor functor.
My goodness, okay.
Okay, I think this has a chance to be true.
That's interesting.
Okay.
So Tian, I have a question actually.
Mm-hmm.
So just following the question of Eric. So okay, you said you cannot turn a rank 4 to rank 5, right? That basically means the MC has the factor Q the rank completely. Does it make sense? So that means like say 4 go to 5, you have to divide 4 to get to 5. That means you have to
I think I don't know. Actually, we should ask.
How could it happen? I mean, this to me, you have to have a fraction which Q the whole rank.
Well, I think we should ask Tian. Do you know this can happen or cannot happen?
Yeah, you can just look at this figure. So rank 4 to rank 5.
No. It's a general question.
No, it's not rank 4. Can you get to rank 5?
It's a general question, not about this ability.
Okay.
So you have the MC have the factor of 4, and then you have an odd factor that completely unrelated to the 2 power. Right? Any odd factor will then could it happen? Can you choose an MC like that extreme?
For one step, it's not that arbitrary. It depends on.
Yeah, it's not arbitrary, right? So there must be some.
But, yeah, so
that may be like less of some factor of n. I mean,
that's right. So, but after many steps, is basically arbitrary.
Yeah, it appears to be arbitrary, but I think when you sort it out, it may not be arbitrary. So,
yeah, so it basically depends on this.
Yeah, I saw this formula.
This
I
thing,
think like you cannot Q whole MC rate as a denominator for. So I mean, can you have a denominator which has contained NC as a factor, and then you put something relatively prime to the denominator of MC?
That's possible in some cases. Yeah.
It's possible in some cases.
It's possible.
Let's say, as Eric said, let's say n is a 2 power.
Mm-hmm.
And then can m be like some odd factor over?
Yeah, it's possible. Yeah.
It's possible.
It's possible. That's like here. You can go from rank 4 to rank 5.
Oh, rank 4 to rank 5. You do have an example like that.
Yeah, that's one step.
Wow.
It depends on the central charge.
This is really extreme.
Yeah.
Anyway, okay, good to know.
I think
like you take a Z5.
It has to do with the central charge denominator versus the quantum dimension d squared. How they go.
Those are abelian, so central charge all integer, I think.
Yeah, abelian central charge or integer. So there you only go to multiples.
Yeah, so actually it's this, the behavior is like this. Every quantum dimension, so they get multiplied.
Yeah, I think that's what happens. Well, it's not true. You can get category smaller, so you cannot. Oh, you can delete some of them probably.
Yeah. They shrink or increase by the same factor.
Oh, I think here what happens in general. I want to ask you. So in general, you throw some of the quantum dimension out, and then you repeat some of the rest, right?
Yeah, let me explain this graph. Maybe please next slide. Yeah. So basically, here we have 3 quantum dimension. So in the root, we have these 3 quantum dimension, each appear once. But in the non-root, so this is the first, that's 1, this is 1, this will be square root 2. So they appear in 3 groups, each is doubled, because the rank is doubled. So to have this, so therefore quantum dimension always appear in multiples. So these two have the same quantum dimension, these two have the same quantum dimension, these two have the same quantum dimension. So that's this table was built. So we can only, these 3 quantum dimension, actually you can read off quantum dimension for every particle here. So that's the structure.
6.
Yeah.
So this is just semi-on tensor easing, some versions.
Yeah.
All right.
Yeah.
Quantum dimension is a double. Quantum dimension just have these 3 easing value, but they, in the non-root case, they just appear in the multiple. Say here is a doublet. They all appear in doublet. Or maybe there's a triplet if and rank became 9. Things like that.
So actually, if you, so for each quantum dimension, actually the number of the anyon types with this quantum dimension multiplied by the same factor MC.
Yeah.
After a step.
Yeah.
And the total rank and the total quantum dimension, they all.
No. How can that be true if that number is a fraction?
Seems it can be. Yeah.
No, it can be true. If original category, those quantum dimensions appear in the multiples, then you can multiply a fraction, then still integer multiples.
Oh, that must be a theorem then.
Yeah.
It must be a theorem that the multiplicity is always has that denominator.
Yeah, that's right.
And that's how you can get smaller.
Yeah, that's right. Exactly. You can see when you're getting smaller, it's always this quantum dimension appear in the groups, and these groups.
Yeah, so when you get smaller,
group can shrink. Yeah.
Yeah. Okay. That I was confused. How can that happen? So,
yeah.
So you can either blow up one quantum dimension to many, or you can take a whole group and
shrink by a fraction.
And make it smaller.
Yeah.
By the same.
Right.
Okay, I see.
So reduction. To reduce that, the quantum dimension have to appear in cluster form.
Yeah.
Then you reduce, each class have same size, then reduce the cluster by some rational number.
Yeah, okay, that makes sense now. I was so confused.
How you can
go up, go rank smaller. So you have to be fat to start with and multiplicity.
Yeah, that's right.